Hey everyone, so I'm Nick Jones from LANL, here to talk to you about science reliability engineering for high performance computing, or how we applied SRE concepts to our local problem domain of running supercomputers. I'm a scientist at Los Alamos National Laboratory. My educational background is in offensive cybersecurity, and I tend to enjoy hiking, gardening, and music. So what I do for a job is cybersecurity, defensive implementation mostly, so like blue team kind of stuff, system architecture and implementation, which is what this talks about, and then I also worry about CI/CD and computing environments for our user-facing stories. So what I'm going to talk to you all about is what is HPC, so what a supercomputer is and the challenges we face, the admin story, the user story, et cetera. How we can take an SRE mindset to that and do some science reliability engineering. How we took that mindset and put it into a stack of actual software that we enacted. Some benefits we've seen, some future plans, and some takeaways for you all. So what is HPC? What is a supercomputer, right? So I think this really depends, depending on site, right? So some companies run a supercomputer locally, some academic institutions run supercomputers. It tends to be really popular within academia, my lab included. It's often local hardware, so it's a bunch of hardware sitting in a server room that people integrate. They tend to be highly interconnected, both within a supercomputer. So a supercomputer itself is an interconnected resource, but it's also interconnected within an ecosystem of surrounding resources. I think there's a lot of similarities to cloud, right? So what I provide to my customers, the scientists I work with, looks a lot like a cloud provisioning schema, but there's also some notable differences in both customer expectations and the mechanics of what I provide. Locally, my organization's goals look like, so our perfect picture here is highly parallel large-scale jobs with an MPI focus, so we're an MPI house. We tend to be CPU focused with about 600,000 MPI ranks, so 600,000 processes running to do one piece of physics. We have a big focus on correctness and repeatability. This is our cannot fail promise, so this is the one thing we can never mess up. We've also got reasonably large attached file systems as our biggest ecosystem service. So this is in the scale of tens of petabytes. I think our biggest file system is a 50 petabyte file system. So in another picture, another way, so this moody picture is also HPC. So this is our last generation of supercomputer and what it looks like. It's just a bunch of racks sitting on a server room floor. There's no hidden magic here, right? Below the floor is cooling and power. Above the floor are air pathways. So it's a normal data center. It normally looks much more clinical than what this picture would have you believe. I think this supercomputer was something like 8 rows deep. So it's something like 50 or 60 racks total. So it's a resource you can fit in a picture. Put another way, this is what our current supercomputers look like now. So it's highly densely packed compute blades. Within each one of these blades, which are vertically mounted, you have 2 compute nodes. So each one of these is running Linux system. And you have the surrounding hardware required for them to do their job, right? So you've got your power management here, you've got your networking closely embedded, and then this all goes into a highly dense rack where you have your cooling distribution, your power distribution, and everything. So it's just really purpose-built hardware, right? Like I said, local hardware. So this results in a supercomputer being thousands of compute nodes. They tend to be closely co-located because light only moves so fast and we're latency bound. They're built to order, meaning that all of the hardware within a supercomputer looks the same, often has special little bits, right? Like we have higher bandwidth memory, or we have larger local caches compared to commodity hardware. And they're closely orchestrated, meaning they're solving all the same problem often, right? So our highest use cases means that one supercomputer is solving one physics problem for some period of time. Off of those thousands of compute nodes, we're managing them with tens of management nodes. So we tend to manage nodes by cluster, right? So a few slides back, that cluster was named Trinity. So that cluster had something like 20 management nodes. And we tend to scale our complexity by cluster size. So smaller clusters tend to have very simple solutions, and as you scale up, the problems you start seeing and solving tend to also scale up, so you scale up complexity. And then we have a couple of user access nodes. So this is really important for the user story, right? So what the users see, it starts off of this, right? It's what they log into and it's how they get their job done. And then also importantly, we've got those ecosystem services, which are also local in our data centers. So this is stuff like NFS and Lustre. Lustre is a parallel file system. So this makes us look different than a cloud service, right? So we can't expand without buying. If I lose 10% of my resources, that means that I now need to put those resources back in physically, right? So there's a lot of realities to the data center that come in with this, right? Like how you onboard and offboard parts of your supercomputer become a worry. Most of our resources are diskless, so in that picture earlier, I think there were something like 30 hard drives total across those 60 racks. So a lot of our resources are diskless. Every compute node doesn't have a disk, as it's another point of failure. Our acquisition and running cost is pretty constant, right? So you buy a supercomputer, big cost up front, a couple of tens of millions of dollars, and then you tend to run it for about 8 years afterwards, which is a lower running cost. We have to manage every aspect of our integrations as well, which results in clusters being pets, not cattle, often. So we name them, we give them idiosyncrasies, and we deal with the complications thereof. Our user interfaces tend to be different. My users don't want to type, kube kettle apply -f or apply a Helm chart to do their science. They want a simple interface for how they do things. This tends to be a pretty limiting factor on complexity. So anytime we change how something works, we always need to keep the user forefront. The user expectations also pretty different. So our users care quite a bit about the hardware they're running on. So they tend to be computational physicists. So right now they're really concerned about the memory and how fast they can move things in and out of memory. We also don't preempt any resources. So once a user gets a resource, it is theirs and theirs totally. So we're not oversubscribing or anything like that until they hit their wall time on their job. However, I think we still look like a cloud service in the end, right? So I'm still in the service bandwidth game. I'm providing compute cycles and simulation storage to my users. So really what I'm trying to get done for my users is get their simulations done and get them stored, right? So they can see the results. We want to saturate what we have. Just because users are getting all of a compute node doesn't mean that I don't want every compute node in a cluster to be taken. Downtime still sucks, especially since our clusters are pets, right? Sometimes people want to do their work on one singular cluster, which means if I take it away for 2 days, I can't float that work anywhere else. And in the cloud, hardware still does matter for really specific use cases, right? So think your LLM models that really want to run on a specific piece of GPU hardware. So what this ends up looking like for the user, so that kind of covered the admin story, right? The user story is purposefully very simple. So shell focused, so they're logging into a Linux shell on a node. They're compiling their stuff, so they're typing make or cmake, right? And they're submitting a job. This job's almost always MPI focused, just because that's what our clusters have resource-wise. Testing tends to use in the scale of 1 to 10 nodes, and production uses hundreds, thousands, or the entire cluster of nodes. That's where that 600,000 MPI ranks from earlier comes. That's just how many processors we have total across our entire production cluster for our largest supercomputer. And in return, they get science at the end, right? So they put a job in, they wait a while, and eventually they get science in return. What science looks like is this. So this is a physics simulation of materials, I presume concrete on a building. So they tend to condense their results down into videos, images, yes, no answers, that kind of thing. So we wouldn't do supercomputers if we didn't have a reason, right? And they come with a lot of challenges and benefits. I'll start with the bad part first. So I'll talk about everything that comes as a challenge, and this is kind of how we targeted from an SRE mindset, what we want to do with a stack, right? But then also we have benefits that naturally come with this architecture. So one big challenge we have is resiliency. So user jobs are often sensitive to a single compute node dropout. So if we're running our biggest supercomputer of 6,200 nodes, if we lose a singular one of those nodes, the user job often dies and we lose hours of progress. And then they have to resubmit and start from their last checkpoint. This very importantly means we can't preempt anything. So it's not like a float a job resource kind of problem. It's a don't lose a job resource kind of problem. It also means that recovering to full capacity is important, right? So our service bandwidth we provide scales with capacity. So we need to worry about mean time to recovery here. We also conversely can't hold extra space for failover, right? Holding extra space means that we could be doing science with those nodes instead. So it's more about having a spare set of blades ready to rack in and replace. And this also means that clusters are often sensitive to a single management resource dropout. So think about losing something like a management node or a core switch or a service interconnect within your data center, right? So if I lose 3% of my compute plane, that can quickly blossom into like 30, 40, 50 total outage, right? Which can really suck. Another challenge is scale. So we have 6,000-ish resources at the top scale here doing the exact same thing at the exact same time. And that's, and the best of times, right? So our purposeful use case is having everything do the exact same thing. So this can have interesting effects on things like your power. So booting 6,000 nodes can take more power than running 6,000 nodes does. So you can boot an entire cluster, not have it all come up. Your power distribution units can start failing. Service uptime, you can do things like run out of file descriptors on services providing files out to compute nodes, which is just a limitation that you have to engineer in. And then also our surrounding resources. A lot of our surrounding ecosystem is almost purposefully DOSable in the sense that a cluster can output more traffic than some of our ecosystem services can intake. This also causes issues for user operability, right? This is one of our primary knobs we turn on our solutions is there are a lot of things we could do to make it easier from the admin side that would make it worse on the user side. And our users are computational physicists, and we don't want to force them to work in cloud paradigms or anything like that. We want them to use an MPI application in as raw of a sense as possible. We also see rare failures at scale, which is really fun. So we get things like neutron hits on hardware. So once you run at a large enough square footage of data center at high enough density, you're going to notice neutrons hitting your hardware and having things like permanent bit flips in your RAM or CPUs returning 1 bit wrong in certain operations. All sorts of like 1 in 10,000 kind of errors that normally would be reason for you to just trash a server once a year in a normal data center. We kind of see it at the rate of like once a week or thereabouts. So another challenge, this is again our cannot fail, is reproducibility. So our users hope for bit reproducers on their code, which can be really hard. They know how physics works at the base levels, right? So they have base use cases, they test with their simulations, and if we get something wrong, they'll know immediately. A lot of artifacts are involved in this though, right? So I've been talking very supercomputer centric, which is where this compute image comes in. So that's our input to their problem, right? But there's also their surrounding programming environment, what libraries they use, what math they're using, et cetera. And also the hardware itself that they're running on. So what does the new processor architecture return for a certain floating point operation? Our solution space tends to be really heavily targeted towards this across the whole way, right? This is what we procure for, this is what we build for. This is our core promise to our users. So we wouldn't do all those challenges, right, without having some benefits, right? We do build supercomputers for a reason. I think our biggest benefit is latency and data scale. So co-location has huge benefits for latency. I think you're starting to see this within LLMs and the such. So light only moves so fast. So if you want to push your latency down really low, you want to worry about how far your nodes are from each other. Very related, our network designs focused on hop minimalization. So one node talking to another node takes at most 3 hops within our systems. This tends to move us like at least a magnitude down lower than a non-purpose built system. Our parallel file systems, likewise, are built for purpose, right? So we have multiple file systems. We have our 50 petabyte file system built for size. We have low latency file systems if you're waiting to continue your science based on opening and closing a file descriptor. We always want our CPUs to be busy, right? We have high throughput file systems if you want to stream some data into an application. And we have high lifetime file systems if you want your data to outlive you. I think if we didn't need the scale of hundreds of petabytes in aggregate of data storage that we write multiple times per day, I think some cloud workflows would look more appealing, right? There's no magic here. We're just building a solution for a problem set. Another benefit we have is we're built to fit. So we know what we're going to run, right? So we have historical physics codes at my workplace, and we know their usage patterns. We know what things they're trying to solve. We know what their next sprints are. We tend to procure for them. So vendors on our RFPs tend to get reproducers for their procurement offers. These come with figures of merit, right? So you can say, I'm running this piece of the solution set this fast. And we tend to target bottlenecks with these procurements. Right now, we're targeting memory bandwidth, CPU clock rate, and CPU cache. So we're interested in moving data into memory, doing some floating point operations on it, and moving it out of memory very quickly, right? Every time we have to do that memory transaction, it costs us time. So this is a chart of what I mean for built to fit. Hopefully it's readable. So on the top, you can see we have 4 different codes. 2 of them are hydrodynamic codes. 2 of them are energy transport codes. The first row is how much memory we need per piece of material. The second row is really important. It's our access pattern. Right, so this is saying we're very irregular with our access patterns to memory, which means that something like a GPU isn't as strong. We're doing a lot of sparse matrix calculations. And then our communication patterns, also very important here. Anytime it says point to point, that means you're doing a neighbor calculation as opposed to talking to every node within a cluster, which is very expensive. So we have a lot of point-to-point calculations, which means we can focus on point-to-point latency instead of all-to-all latency. And then on the bottom, it's just how many operations we need to do on a piece of data before we move on to the next piece of data. So in general, you can see our memory needs are pretty small per cell, and we have lots of cells. We're doing a lot of irregular access, so we need things to go quickly, right? We're concerned about working on these individual pieces in parallel very quickly, which is why we end up with such a CPU latency-focused solution set. So we take all of these bits and then we put them into an SRE mindset. It's kind of the idea of this talk, right? So science, reliability, engineering. So how can we take those benefits and those challenges we face and make a solution set that solves just those, right? How can we not eat every problem in the data center and focus on making these bits better? So we got to start somewhere, right? So we start with these boutique deployments. So our RFPs often end up with a vendor delivering exactly what we want for everything in the RFP. They have tightly coupled management stacks, so we have a whole bunch of tightly interconnected services, and they end up being very concentrated, right? So I'd said in the magnitude of tens of nodes, it can go down as low as like 1 for very small clusters, 6 for medium-ish clusters, and right now we're at like 40 or 50 management nodes for our 6,000 node cluster. So this is realistically a very concentrated management stack that's very coupled. A lot of our system changes start with a downtime start, right? So downtimes are painful. We don't want to take systems away, which means we test on canaries and then we prep all those changes. And when downtime hits, you have a person typing on a keyboard to make those changes. A lot of this is like resiliency through simplicity aimed. And it really ends up being a very heavy hands-on keyboard process for service, downtime, and patching, right? So there's a human doing all of these things in real time when it's the downtime. So this comes with a lot of issues, right? So boutique means unresearchable, often closed source. So if I get paged at 2 a.m. and I have to go in and fix a cluster and I hit a local like vendor solution, I can't just Google it in many cases. I'm stuck running like strings on a binary or putting in a ticket at 2 a.m. that I know is not going to be answered till 10 a.m., which extends our outages, right? And our primary metric here is mean time to recovery. So 8 hours added on to what should be 3 minutes is a pretty bad mean time to recovery. Our concentrated management stack means we can bloom those partial data center outages quickly into total outages, right? So we can lose a little bit, cause more pressure on the management stack. It's not a very flexible management stack, which means that you put more pressure and suffer cascading failures at scale. And for example, we live at pretty high elevation. So my server room's at like 2,200 meters elevation. So it comes with a higher rate of lightning strikes. So we have a good amount of brownouts during monsoon season. And in general, our risk and cost of failure is pretty extreme. So we have this heavy hands-on keyboard process where somebody's working on a supercomputer, and you have hours before preparation, hours during downtime of running playbooks. And if you suffer a failure, right, you're repeating every single one of these hours while still withholding a resource from your customers. And every human action we have on this is another chance for failure, right? And this results in a really high human cost for running a supercomputer. It's really hard to iterate and change what you're doing. It's hard to onboard a new supercomputer, change how it works, or hire someone new. So we wanted to take some SRE concepts for this, right? How can we take what we have right now and redesign it to be a bit more sustainable? So we wanted to be open source, so things are actually Googleable. We wanted to take those design metrics, right, what challenges we face and what benefits we get, and actually design our resources around those stories and figure out how we can treat them as problems to be solved with inputs and outputs. We wanted to look into being modular so that if we need to switch to another open source solution or something stops being supported, or all 6 maintainers on a project get hit by a bus, right, we can switch that piece of the solution. We wanted to be API driven so we can respect machine workflows and human workflows at the same level, which helps take the human hands off the keyboard. We wanted to be OS agnostic so we are a bit less tightly coupled. And very importantly here, I think this is a big point of SRE, we want to be very disjointed with our actions, right? We wanted to focus on artifacts, so artifacts that go in and come out of processes, right? How do I boot and run a supercomputer, and how can I treat those pieces as artifacts and things that I can run unit tests on? And we want to disconnect the creation of these artifacts from the usage. So we don't want a Rube Goldberg machine in the end, right? Here we want a set of processes that act like functions. And all of this working ahead means we can check as we go. So the whole idea is to move left on this downtime, right, and reduce that risk. So like most people, we wrote a stack of software. It's called OpenCHAMI. It's on GitHub. It's just github.com/OpenCHAMI. I think it's a backronym, so this is what it stands for. Open as an open source, composable like Docker Compose, heterogeneous meaning we're not locked into the exact stack, application as an API, and most importantly, management infrastructure, like the thing that's running the supercomputer, right? So that's what this thing's job is. We're not trying to eat the whole ecosystem, we're just trying to manage the hardware that the supercomputer runs on. So I'll dive a bit deeper in on that. So what we're interested in is component enumeration, right? So what does my supercomputer consist of? What nodes do I have? What firmware do they have? And how do I manage their boot lifecycle? Specifically on the nodes themselves, I'm interested in building them, physically racking them into the server racks and seeing what happens afterwards, right? How do I go from something requesting a PXE boot to knowing what I should give it and giving it that? Deploying onto those compute images at scale, reproducing my results. So if somebody says, I wish it was October 10th again, the goal of this is to bring them back to October 10th resource-wise. And very importantly here too is reusing what we have. So not treating clusters as pets, but instead cattle. So seeing what resources we can share across problem domains. And then also cryptographic root of trust, ensuring somebody doesn't plug their laptop into a supercomputer, act like a compute node, and get a full image. So what this looks like in practice in a deployment is it's just a collection of microservices and Linux services and containers. Like I said, there's no magic here, right? So our microservices are written in Go. We chose it for its parallelism and its portability. It's engineered to fit those needs from earlier, those challenges and benefits, while being reasonably minimal. It's container focused via Podman for our local deployments. We just tend to be a Podman house. That's what we went with. It's like 17-ish containers total, depending how you look at it. But we're realistically container runtime agnostic. We're not attached to any CRI feature or any CNI feature. Our generated artifacts are all open source, signed with GitHub SigStore, all normal abstractions, right? We're like Salsa 3 or something like that as far as provenance goes. And we're aiming to scale horizontally through many failure domains rather than vertically through a singular large stack, which is kind of one of our stakes we've put in the ground, right? This is us attempting to fight that complexity growing with cluster size. So this is really making it small, right? So we've taken a lot of things that are actually part of a supercomputer and totally out-of-scoped them. So we're not worried about how to manage the network or build the images that result in a compute image. We're not worried about our programming environments that get mounted on the side or how logging and metrics works. Same thing goes for workload management and IAM. All of these things we're treating as surrounding services with inputs and outputs. We can give them promises, we can take promises from them. But really importantly, we're trying to keep the stack small and focused, right? We're trying to answer our user and admin story that we have. We're also trying to fit in our ecosystem, right? So very importantly here, we're not reinventing the wheel. So this is why we've stuck with Podman instead of moving to Kubernetes or something like that, right? We currently use smaller container management frameworks and we have no application need to move, right? So there's no problem that we have to answer yet that requires a larger framework. We've also only been writing new things when needed, right? So there's no reason to reinvent the wheel on DHCP. There's like 6 supported DHCP servers, so we can just use any of them. And we're relying on all of the surrounding abstractions that are available to us, right? So this is stuff like GitHub Actions. Our compute images come from Builda. So compute image in our case is just a squash FS. Builda can build squash FSs. So we can hire people that use Builda and we can't hire people that know what a squash FS is. So we've leaned towards Builda. And we're also using Go libraries in this case, right? We can share common functionality. We don't have to reinvent the wheel on how OAuth 2 works. And importantly, we're using our existing configuration management and infrastructure. So we already know how to run Linux boxes. There's no reason to toss out that work. We're only changing part of our workflow, not the entire thing. So before I talk about how good it's been, it comes with a bunch of pain points, right? So scaling wide via different failure domains isn't easy. Moving from 1 pet to 10 cattle per cluster means that you have a lot more small failures. There's a lot more initial churn while you learn how to automate these problems away, right? Having 1 giant pet with 1 giant problem does still mean you only have 1 problem at a time instead of 10 at once. Interacting with the hardware has been kind of terrible. So doing things like booting stateless nodes takes a lot of privilege, and figuring out where exactly to put that privilege and how that fits into your security model is pretty hard. And just in general, moving from pets to cattle is really hard, right? So you run into things like treasured processes that need to be cut. So we used to use a mono repo for our image build and our post-boot configuration management. That kind of sucks for reproducibility. You walk them at different rates. You can run new configuration management on an old image, things like that. It makes for a lot more combinations than walking them separately. So you just say tag A plus tag B on both pieces. Reassessing our assumptions, right? So this is where those benefits and challenges come from. Why are we doing this as we are, right? If you strip away the programming environments and the surrounding file systems, why do we run a supercomputer the way we do? What questions are we actually answering? And overall, it's meant a lot more time designing and less time administrating. So sometimes you design something and it doesn't work out super well the first time and you have to go back to the drawing board. And you only hit that after you've been doing it for a while, right? So it means that you're gonna spend a lot more time redesigning things than you expected to. But we've seen a bunch of benefits, right? So taking a different problem domain and looking at it through an SRE mindset's been really helpful, and especially when it comes to making that into a solution. So our installs are single day now. They used to be like 2 weeks. This comes with learning curve, right? It's a stack that you have to learn. So I don't think anybody's done that their first time yet. But the general point is there's much less human work to be done in instantiation of a supercomputer, at least for the boot plane. This comes with nuance, right? Once you out-of-scope so many things, those things still need to get done. So we still need to do things like configure the network and worry about what image is building and make sure that we deliver the science in the end. Those just get put into individually smaller boxes. We've also moved the window left on a lot of downtimes, meaning that all of these separate pieces, right, so the operating system we're running on the management stack, what we provide as a compute image, all the surrounding ecosystem services get treated separately, right? So we're solving 10 littler problems and suffering smaller failures across our environment. We're building these pieces as soon as code is committed on a mergeable branch, right? So this is just normal CI/CD. We know right away with a reasonable good gut check whether something's gonna work or not. And we're doing this on commit, not downtime, right? So it means that we're discovering a large class of failure cases that would have happened live way beforehand. It also gives us a lot of resiliency to the industry at wide, right? So we've made a lot more of our things look like containers, which lets us take advantage of a lot of the surrounding community abstractions. And it also gives us the ability to switch from deprecated or unsupported software, right? We're not like desperately tied to a vendor when we buy a supercomputer. And just in general, it's been really good for community involvement. So if we use a tool and we want it to change, it's open source, so we can always open a PR. So a quick example of what I mean by CI/CD. So this will be a pretty quick, simple example. So we use Builder for our images, like I said. This is me adding a text editor to the base image of a compute node. Compute nodes get personalized via function and cluster and fabric and all of that, right? So I make a quick commit on a mergeable branch. It spawns off a multi-stage job on our local GitLab instance. You can see 5 stages here. It initializes the environment. It makes that base image. So we're afraid of side effects in this case, right? So even if I just change something in the base image, I want to replay everything else on top of it just in case. And then I add my fabric drivers. So in this case, OPA, InfiniBand, and then I customize it for input, output, and compute. So just by me making a simple change, immediately a build gets kicked off. I have an artifact that I can use later down the line. And like I said, it's quite literally just Builda. If anybody's used Builda, this is quite a bit of Builda output. We do need a little bit of extra glue on it because we need both a kernel and a init FS, which containers obviously don't have. But the general point is, right, we can use a community abstraction to solve our local use cases. So that kind of covers what we've done. In the future, we want to aim for sustainability, right? We currently have a small sustainable solution and we'd like to keep it that way. Which means we want to look at our boutique solutions and look at the worst pain points that we have and take some small parts of our current stack and move it to our previous stack. We want to keep involved in the community, right? So if we want something to move towards our use case, we can always just open a pull request. And we want to involve more open source pieces, especially ones that we don't directly maintain. So for example, our TPM management's a piece of terrible Python that I wrote, and I'd really like to not support that. So figuring out something for that would be really good. And also close to that is our boot lifecycle management, right? How we turn on and off a cluster. And we also need to scale bigger. We're currently at the magnitude of thousands, and it would be nice to have tens of thousands. We're aiming to solve this with horizontal scaling, so it's not like some crazy engineering problem or anything like that, but it's just a fact of what we need to do. And a quick example of what I mean by sustainable, so hopefully it shows up pretty all right. So we're in Podman Quadlet, so everything in blue is a daemon running in a container under system D. So those are permanent resources. Everything in green is a one-shot resource. So we're only at about 12 permanently running resources to run a supercomputer. Some of our biggest supercomputers right now look more like 300-ish running resources, so we've cut down at least a magnitude in our scale of complexity here. We also want to keep scoping for impact, right? So it's all about our inputs and outputs. It's all about solving the problems we have and making sure we naturally benefit our users. So this is things like node lifecycle management. How do I ensure that when I rack in a node, it's a pleasant process for the admin? And also post-boot configuration management. This is a treasured process we've cut, right? So it's no longer a mono repo, so we need to make sure the admin story is good on it. We also need to empower our surrounding services and workflows. So we want to empower the things we can't scope in, right? So image builds are very core to what we take in, but we don't manage it. But we do want to make sure that we can take advantage of whatever abstraction exists. Same thing for workload management and all of those ecosystem services, right? How can we make our file system teams' lives easier? How can we make the programming environments teams' lives easier? So if I leave you with any takeaways, it's pay attention to your surrounding industry, right? So for us, it was microservices. Why do people run microservices? How can you treat things as inputs and outputs and put them in smaller boxes? Infrastructure as code, especially ways we can reuse it and abuse it for reproducibility, right? The container has a SHA hash, we know exactly what's in it, and you can point towards the hash and say, yes, I know what this is. Hardware adaptability and how people are adapting quickly to new hardware stacks in the cloud. Stack flexibility, right? How people are taking little parts of their stacks and moving it in and out. And then engineer around your success metrics. I think our local success metrics look a little bit different than a common SRE metric, right? So we're primarily concerned with reproducibility, which we've solved with this artifact-based workflow. Downtime minimalization, especially mean time to recovery, and single node resiliency. All right, that's what I got. Thank you.